The next talk is entitled Impact of Autonomy on Transformative Transportation and Logistics. Kaydon Stanzione is going to give the talk, and while he is getting ready, let me introduce him. Kaydon serves as the CEO and Chief Scientist of LogistaWorks, which is a transformative logistics company currently managing roughly 5 billion pounds of freight throughout North America. And so we have a really interesting similar scale problem, right? 5 billion pounds of things we have to keep track of at all times. It sounds like a tremendous opportunity for nano-enabled Internet of Things. He started his career as an air vehicle designer, worked with a number of companies associated with both military and commercial aircraft design. Has authored over 150 papers in various journals, including Encyclopedia Britannica, so literally writing the book or the article on aerospace engineering. So he's leading LogistaWorks in the development and integration of autonomous load handling and multimodal carrier systems, and we're very excited to hear how Nano IoT might be able to help out in this area. So I think I may need to ask Sherry to stop screen sharing so that Kaydon can start.
Thank you, Mark. Can anyone hear me?
Yes, we hear you. Great.
Great. Can you see it? Can you all see my screen?
We see you and an impressive looking jet behind you, but
just a former toy. I've shared the screen, but here we go. We'll try it again. How about now?
Yes, that's perfect.
Okay, great. Well, thank you, Mark, and thank everyone for attending. And Sherry, I really enjoyed that presentation. I did send you a question. I know you don't have time to answer it, but perhaps you can take a look at it later. Really enjoyed that. So connected logistics, the impact of autonomy on transformative transportation and logistics. So everybody tends to think of logistics as, hey, I'm going to order something from Amazon and it's going to show up on my front door. Well, if you've been ordering from Amazon over the past few years, you're going to realize you can order at 8 o'clock in the morning and sometimes have it at your front door at 10:30 in the morning. And there's a massive process that goes behind the scenes. Now, one of the typical things is the placement of warehouses. But just as manufacturing experienced a technology boom years ago by doing just-in-time manufacturing, what we're seeing today is just-in-time logistics. And of course, logistics as a service, because there's a lot of elements that need to be managed. So let me, so just a little bit about our background. We actually just started the operations in March of this year. So we're ramping up very rapidly. A lot of that has to do with an extensive R&D investment over years, pushing close to $40 million, and testing in very remote areas, Africa from Lagos, the Sudan, Egypt, all throughout India, where transportation has tremendous challenges. I have a small operation looking at Thailand, outside of Rayong, and we're also looking at Singapore because there's been some dramatic shifts with the closure of a lot of the logistic channels with China and our big trade deficit with China. It's moved into Singapore. We do have patent protected production grade solutions, obviously, and what we have really developed was providing the logistics as a service so that disparate third-party, non-connected participants can actually communicate seamlessly through a single sign-on. And that also allows us to do the logistics aggregation, where there's a seamless, what we call a switch out or a relay, as packages and vehicles move from one domain to another. And we provide a toolkit to try to understand how this gets done. So when we say transformative logistics, and I want to take it down to transformative transportation. And you've probably seen this if you've been in some cities like Atlanta or some of the other cities. The e-bikes, electric bikes, pedelecs as they'd be called, started taking off. That's kind of died out a little bit due to some safety issues and some other regulatory issues. But everything's changing, right? Land, air, water, rail, bike, off-road, human transit. That's long-tail bikes. It's all changing. So the ability to move product, people, or payload, if you will, better, faster, cheaper, is becoming a reality in a large part because of electric vehicles and how that impacts the design of vehicles, and autonomy, which comes hand in hand with sensors. And then overlaying all of that is regulatory processes, which could either assist in the facilitation of this transformative logistics world, or it can impede, depending on which way these regulatory processes go. So some of the challenges that we're seeing, and I want to talk about this because I'm coming from an aspect where I have design centers, we have manufactured sensors. I come from the world of being a pilot, and in a pilot having communications with air to ground, air to air, around the world in real time becomes very important. It also, situational awareness, interoperability, a common operating picture. These are critical facets to save one's life, whether it's a first responder, it's in an operating room, it's in being a pilot, and we do it in little ways, just driving on the highway. The typical example of a child's ball comes across the street. You have to make sure that you sense that, you see that, and you react to that. So, understanding the application of where these technologies can be used and how are we going to get there. A lot of verbiage on autonomy, right? We're going to have pure autonomy. We really need to understand that and understand the growth process, the roadmap to get to autonomy. And it affects so many elements that are important in the chain, particularly in this chain, the supply chain. So some of the challenges is omni-channel distribution, right? This is really affecting the dock-to-door problem. And shipping, the transportation has to be so low cost, you just include it in the price of the product. Now that's what Amazon does. If you're looking at players in the space, the big box retailers, Walmart has started a program, and that's an at-home type of a program. It's Walmart Go. And because they have retail and warehousing space, they're increasing their vehicle assets to be able to compete with Amazon. And also large carriers like SD's freight lines that have 30,000 vehicles that typically just move freight from a dock to a dock. That's called a less than load or full truckload of freight. That's forklift on, forklift off. Well, they've recognized to compete, they now have an at-home delivery service and a white glove service. That means they're now transporting goods and bringing it into a residential area and actually bringing it into the house and setting it up. All of this becomes possible of a complex network of sensors and software and communications that has to work in real time. Now that's just looking at land transportation. What happens when you're multimodal and you're going to look at different modalities of transportation? So the secondary industry challenges that we are seeing is, electrics bring in that low sulfur, carbonless, footprint. The demand volatility, it fluctuates like crazy. So how are you going to support fleets that may or may not have what's called line haul, going from point A to point B all the time? When you commute to work, you may commute via a particular route. Think of that as a line haul. But if there's a detour for whatever, you may use Waze or some other app, but you'll find an alternative way to go. It's not your preferred way. You're not going your line haul way, you're going an alternative way. Well, when in a previous company that I co-founded, which is an urban air mobility company, an electric aircraft company, we were one of the 6 original Uber partners for urban air mobility. The concept there was building an aircraft that will now fly over traffic. It'll shortcut, the roadway system or the railway system, the ferry system. And you can do that by traveling as the bee flies, right? As the crow flies from point A to point B. But a lot of the challenges that we have, like I mentioned, from just-in-time manufacturing, means that now you don't want to have warehousing. If it's coming off the manufacturing line, you want to be able to ship it immediately so that you're not overpopulating your manufacturing run. You don't have product that's sitting on a dock somewhere or a warehouse. You don't have to move it to a third-party warehouse. You're going to load it onto a vehicle and take it somewhere. And again, that gets into eliminating warehouse constraints. You get rid of the road congestion as you go to electrics or hydrocarbons or fuel cells. You're reducing the fuel cost. And then the other problem that we're really running into is the labor shortage and the increasing labor rates that are making transportation very expensive, again, whether it's people or packages. So I mentioned autonomy. We need to understand autonomy. You probably have all seen this at one point or the other, at least thought about it, but let's put it in terms of cars and robots. Okay, so I've had a Tesla Model 3, fascinating car. You can put it on the highway. It'll take you off the exit ramps. It'll slow down in traffic. It'll change lanes for you. When you put it in local road, it can detect traffic lights, stop signs. It'll slow down. You're always the driver in the loop, DIL, and it's a smart vehicle. But that's a smart vehicle because it uses a series of electro-optic devices, cameras, CCD type cameras, and other sensors, LiDAR, sound, acoustics, ultrasound. So a series of sensors are being used and being processed, right? So it becomes one of sensor fusion, data fusion, processing that data. There's no true intelligence into the autonomy of the aircraft, of the car, but a lot of people tend to think that the Tesla is an autonomous vehicle, and its marketing kind of pitched that way. But let's just take a look. Level 0, whether it's a robot, and think of an automation system inside a warehouse, in a factory, in a distribution center. So there's no automation, that's 0. So that's your basis. As you get to cars, level 1, you still need a driver assistance. So you may have a new car where if you're coming up tailgating someone, you're getting a little too close, it'll flash a signal, an LED, and provide an audible sound, and you need to then slow down. So you still need to do something to remain safe. With robots, what happens is you immediately go to some level of autonomy at a level 1, but that's still a direct line of sight, a DLOS. So you still have a direct line of sight of the robot. Think of a remote controlled airplane or remote controlled car that a child may play with, where they have a joystick. They're still looking at that vehicle that's moving and they're controlling it. So there's some level of autonomy. Then the other thing we need to do is to take a look at the intervention time, and that's the intervention time of when a human needs to be involved. So from a driver assist, it has to be immediate. At a level 1, it has to be immediate. With a robot that's, let's call it remote controlled, maybe 5 minutes. And these numbers on intervention are coming from the fact that we have tested this out in cars like Teslas, in robots, in flying machines, in ground-based machines, in water machines. And we've done a lot of testing down at the Georgia Institute of Technology in understanding some of this. When you start getting to partial automation in cars, that is going to be the equivalent in a robot of beyond line of sight. So now you can send a robot out there and you're no longer seeing what it's doing. So it is starting to have more and more sensors. This is what I'm going to use as a framework. This is your Tesla. car right here. And there's other cars, Polestar and other cars that are coming out with more and more levels of sensor and data fusion that are giving you a level 2. I put a 2+ in there because some organizations like to say, well, you know, I'm driving a vehicle and I have some partial automation and I have a driver in the loop. It's not one of the 5 levels, but you may see it out there. So now the next level that we need to go to is 3, conditional automation. And now we're getting in autonomy, it's more like robot farm supervision. If you've ever looked at an automobile manufacturing facility, you'll see a lot of the one-armed robots or multi-armed robots in a production line, you know, building pieces and doing things. These are very well-trained machines. They're trained because they're programmed. They're still not making their own decisions, but they are learning things that you take the database and then the coders go back and they reprogram the rule set, if you will. And what happens is in the conditional automation from cars, maybe you have 30 seconds without a driver in the loop intervention. That's something that you have to really think about for a second. If you're driving in the highway and you're driving in traffic, you probably have been in that position where you might have been sidetracked by a noise or a flash of light for a second, and you refocus on the road, and you might have to, you know, make a quick adjustment. So 1 second, a 1 second drift can be very critical in a vehicle, depending on the speed and where you're at. So think about being able to go 30 seconds driving. Now, if you're on a major highway with no traffic, that's one thing. But being in a city or any kind of suburban area for 30 seconds, not paying attention and letting the machines do the driving, that's a very, very long time. That's a big challenge. And we're not even there yet. Now, for robot farm supervision, yeah, you can do that. You can do that for 8 hours. These robots will work all day. So it's a little bit different dynamic. And just following it through as you take a look at high automation and full automation being no driver in the loop, obviously there's economic advantage. You know, the cost, for example, the cost of freight, a lot of it, I'm just going to give you aggregate numbers, but the cost of freight is about almost half is due to having an operator or multiple operators in the loop. And the associated cost of the operator, the insurance, building vehicles that it can accommodate these operators. So 50 cents to the dollar is going into you know, having an operator in that loop. So where are we looking? You know, we have a lot of problems to solve here. We are looking at autonomous vehicle technologies, but it doesn't mean that we're going to be able to get there immediately. We need to provision for them, and we need to understand how the business is changing. A good part of it is in robotic freight and packaging. So whether or not you're looking at replacing batteries, and again, there's high-speed charging for if you have an electric vehicle, there's a lot of high-speed charging ports, not a lot. So you have to plan how you travel around how you can charge your vehicle. For cars, it's one thing, but for commercial vehicles, they charge differently. And for commercial non-land vehicles like watercraft and aircraft, they have a completely different charging infrastructure. So even if you were to build these aircraft or introduce them today, these air vehicles or land vehicles or water vehicles today, the charging infrastructure may not be there. So therefore, you have to design your logistics so that it's a round trip. So it goes out to a bingo point where it still has enough energy to be able to return back or return to a point where you can then terminate your travel and then recharge. So doing all of this now means we're going to go intermodal. So intermodal, think of it as if I want to have a package that or freight that can go, let's just take our Northeast corridor. And let's take it from New York City to Washington, D.C. right? We're going to pick something up in a small van. We're going to then transport that to an area where it would go perhaps into an LTL freight, a 53-foot tractor trailer. We're going to drive that. And if it's got to be residential, we're going to drive all the way down to the DC area. And then we're going to go to what's called a cartage agent. We're going to offload that, put it in a smaller truck that can then be taken into a residential delivery. Now, if you take a look at what are the intermodalities, how else could this be done? Well, companies like Flying Ship are looking at ground effect vehicles, which are really maritime vessels. So they can come down the waterway at 200 miles an hour. Electric aircraft, they could just fly direct. And instead of having a 4-hour flight with all those changes in fuel costs and carbon footprint and everything else, they're going to do that in roughly 30 minutes. So, you get the time value of money, and you have to start to understand, how are we going to move all of this, freight? How are we going to move packages, small packages? And we need to communicate that. So if we're going to, right now, even in land transportation, going from a dock to 1 or 2 different types of vehicles to a different dock to then an unload, all of that needs to be communicated in real time. And we need to understand, what the vehicle is doing, what the driver is doing, what's the capacity of the vehicle and driver, and what equipment are going to be at each end, robotic equipment to load and unload this technology, the packages. So it gets down to control systems. And this is what becomes very important. So in the aircraft, for an FAA certification, it has to be, well, they all have to be high reliable, low latency, but high determinism. It has to be a deterministic solution. And there's different bus protocols that are used to communicate the information. In the military, it's a Mil Standard 1553 bus. That became commercialized to an A-Rank 429 bus. They've tried to simplify that. Okay, when you start getting into these characteristics of control and communications, you're also going wide area network through satellite or cellular, or even in certain locations, we are now doing with our own sensors that we manufacture, VHF and UHF frequencies, where we can communicate direct. And it's not just in the ISM band and the 900 frequency range, but sometimes you have to go very low. For example, we put a lot of sensors into water processing plants and facilities, and found that we have to be at very low frequencies to get through all the carbon and steel. And that, those sensors are usually electromechanical sensors to automatically control valves and water flow and chemical flow, but also to be able to communicate with replenishment trucks and safety personnel and shut down gates. All of this has to be communicated in real time. But if you follow the technology, you really got to get into the policies, like deep deterministic policy gradients. And how are you going to get there? It's very, very complex. So what we saw at an early stage was a CAN bus protocol. And we saw that, we're going to eat this elephant one bite at a time. We want to get to autonomy. We'll provision for autonomy, whether it's in load handling equipment and any of the transformative vehicles, whatever modalities they may be. And we want to make sure that we can communicate the information fast enough with low latency over any one of the available networks, whether it's wireline, but here we're really looking at wireless. CAN bus came out in the mid-1990s, I think 1996 it went into production. But CAN bus is a 2-wire, which seems to be very simple protocol. Okay, and it really allows these diverse microcontrollers and devices to communicate without a host computer. That becomes clutch. So as we were developing in another company that I am involved with, as we were developing urban air mobility, all electric vehicles, we were moving towards CAN bus in that vehicle. Now, when we built drones, whether they're land-based drones, water-based, air-based drones, Again, we moved them to CAN bus. So when we start moving things to CAN bus, we can get onboard real-time diagnostics, because we can pull what's called, if you did the research, it's pulling the PGNs and the SPNs, but we understand what the vehicle is doing. If everything is on that CAN bus structure, we know if a tail light is out, we know if a sensor's not working properly, or if it's failed. We also know how to program these sensors if we have a two-way communication channel, which we have built, so that the sensors are edge devices. So you just don't put a sensor out in the field that's sensing something passively. It needs to be a two-way communication sensor that has the ability for analog and digital inputs, as well as analog and digital outputs. So an example would be in fire coding, which would be if you had a sensor that senses heat, that's transmitting that all the way back to a central processor somewhere that makes a decision. It says, turn on the sprinkler. Well, what happens if that wire's cut? Because they're all wireline. That's by fire code. I'm just trying to give you an example. But what happens is if you have an edge sensor that's smart and it can communicate and it has firmware and an intelligence in that sensor, and it's connected on top of or embedded into an electromechanical controller, like a valve that turns on the water sprinkler, then when that particular sensor detects a fire condition, it can immediately turn on the sensor. And if all other networks fail, you're still going to put the fire out. So what happens is we need to be able to communicate with all these different devices in real time, so that what happens is you have zero, minimized downtime, where you're bringing either a land vehicle that's either going to make a pickup or a delivery. So something is coming off production, you know when it's going to be packaged, you have an idea of the ETA time to the dock, you have a vehicle that's going to pick up, or a forklift or an automated robot that knows when to get it and will know where to deliver it. So it goes literally in one smooth, continuous movement. Then it goes from there to, let's say, a land vehicle, and that land vehicle will then at some point want to offload to an air vehicle or a maritime vessel. That would be done robotically, so that the dock end and the transfer vehicle is ready to receive the handoff, or the switch out, it's called, or the relay. Think of a baton in a relay race. And the robots are all ready to put that all together. That's where we're headed. And that is going to be done. Well, okay. It's being done. Yes.
Sorry to interrupt. Yeah, could you give it another minute?
Yeah, I'm just wrapping it up.
Okay, great. Okay.
Yep. So the obvious is autonomous freight handling equipment. The not so obvious is interoperability. And the more not so obvious is interoperability between equipment and all these multimodal transformative types of carriers. So this is what's really happening. You've got to integrate all of these modalities into one seamless operation, from load handling to whichever way it may travel. And things are going to start to travel by different modalities. And then the risk, regulatory processes can kill this. Maturity between where we're investing in road, rail, aviation, and shipping. They're all different levels. There's not really a harmonious integration. The operational domain and where the TRLs, technology readiness levels are, and manufacturing readiness levels are. And then finally, we need to prioritize where we're going to make the investment into artificial neural networks, decision support systems, and migrating towards autonomy. Thank you.
Wow, Kaydon, thank you very much for that presentation. I think I at least gained maybe the tiniest appreciation for the scale of the infrastructure behind, as you said, calling up Amazon and having a package delivered a couple days later. I would like to take the host's prerogative to ask a question. If I think about what you've presented, in my mind, it sort of assembles as a hierarchy of things, starting all the way down with here's a sensor that sends out a little radio beacon, perhaps saying, hey, my package is over here, all the way up to the machine learning analysis of how to make all of these physical flow streams operate most efficiently. And there's all these levels in between. And I'm wondering from your perspective, where you see the potential need for future research. Do we need better sensors? Do we need better communication? You alluded to the problem of getting through steel containers and being able to talk to things that are inside. Do we need better real-time communication between all the logistics nodes? Where do you see the pain points, and how can nanotechnology help?
Right, that's a great question. So, for example, on our multimodal sensors, their footprint is 1 inch by 1 inch. And on that sensor package, that multimodal sensor, we have about 8 different sensors. There's a lot of sensor technologies that are out there, but from our perspective, where we're looking at is the microprocessor speed, right? So going from Atmel microprocessors to like ESP32 processors, and being able to get low cost computational capability and built into the firmware. So what's happening is, instead of just, processing data, IO data, and then having, stacked layers of software on top, all the intelligence needs to be right down at the chip level. So we're burning it all down into firmware because the decisions have to be made, in microseconds. So, to me, the big push is working with the microprocessor companies, understanding how many MIPS we can get out of them. And then from that particular point, it's going to be into the latency of the network. When we're looking, the first presentation was wonderful. Let's just take that agricultural, because what happens is when you start putting sensors in the ground, right? How are you going to communicate with them? There's a protocol called Zigbee, which is a mesh grid protocol that operates at the 900 band for the most part. Some are, well, actually, they're operating at 2.4 gigahertz. But when you're at high frequencies like that, you have a really tough time communicating in traffic. So putting soil sensors down, you really have to take a look at a lower frequency range and the ultra high frequency. You have to be able to process it differently. And you also have to make the sensors, that are going to be able to detect the things you want to detect when they're substantially underground. It's just like having them underwater. About 70 feet underwater, you can't transmit. We have to put an antenna up there. And we do that in some of our submersibles. We float an antenna right below the surface of the water. So those are some of the areas that I think really need to come in to play. But the sensors, you know what? Utilize the sensors that are there. Put the money where it could be most effective. And like Tesla did a great job. They've used traditional sensors. There's about 4,000 different sensor types out there that we can tap into. And, again, of course, it's going to be the mathematical algorithms that you can burn into the firmware. I hope that answers your question, Mark.
Yes, that was very helpful. And what I translated that into in my mind was perhaps where we could be of assistance is in what we call heterogeneous integration. How do we co-locate sensing, microprocessing, power, all of these into continually shrinking and lower cost packages to allow these communication nodes to continue to improve. So
absolutely. And you mentioned energy, and just giving you an idea, we use lithium ion, and our sensors operate, they transmit 17 times a second for 2 years nonstop. So we don't have to replace the battery or the sensor. And that's in an IP68 environment. So that's something you also need to be considerate of, is the energy consumption.
great. Well, thank you again, Kaydon,